great. And you get, okay, I was not trying to draw extra attention to you. Alright, so test corrections and the reflection, if you're done with them, put them in the middle of the table. Otherwise, you have until 2:30, and that's because you're going to stay with me from 1:30 to 2:30 today to do that. Polymon and Lewis, letter of recommendation request form?
I didn't print it out.
You didn't print it out. Same. I'm not going to write anything until I get your request form. However, Celeste and Stephen, I will have your letters tomorrow so that you can review them. You can provide me any feedback that you want. You can also make donations to Caroline's college savings account. You can leave, all sorts of tributes on my desk. That would be fine there.
Can I also get a form just to get a form?
Can you get a form just to get a form? Because I like writing letters of recommendation that much. No. All right. Homework tonight is L'Hôpital Day 2, problems 1 through 6 and 9 through 12. These are BC only kinds of questions. These are the hard ones. Last night was supposed to be the easier ones. These are in the problem set. It says L'Hôpital's Rule Day 2, 1 through 6, and 9 through 12. Correct, not 7 and 8. These are in the problem set. All right, last night's homework. Here we go, quick like a bunny. All right, if you could you can tear out those problems from the packet. All right, problem number 1 is C. We already did this one yesterday. Number 2 is B. Also did that one yesterday. 3 is C. Everybody okay with that one? Yeah. 4 was A and 5 was C. You guys knew that before you left yesterday. Number 6, B. Number 7, D. For favorite math teacher ever, DeRozier. 8 is B. 9 is D. I'm curious, looking at number 9. If you didn't know L'Hôpital's rule, what is it that I'm really asking for in number 9? What am I really asking for in number 9? I see Stephen. I see Celeste. I'm worried about the other 9. David, what am I really asking you for in problem number 9 here? I'm asking one of those sneaky derivative questions, right? I'm asking for you to find the derivative of sine of 2x at x equals 0. The derivative of sine of 2x would be cosine of 2x times 2. Evaluate that at 0, you're going to get 2. Same answer. L'Hôpital's rule isn't giving you new answers, it's giving you a new way to evaluate old problems. All right, number 10. Ooh, horizontal asymptotes. Horizontal asymptotes. You're going to take the limit as x approaches infinity. You're going to take the limit as x approaches negative infinity. The correct answer here should be E. Number 11, E. And number 12, D. Are there any of these that we need to talk about, or they all go pretty well? 10. Number 10, the line y equals 5 is a horizontal asymptote to which of the following functions? So to find horizontal asymptotes, Myra, I'm going to ask myself the question, what's the limit? Right, horizontal asymptotes, you're always asking what's the limit as x approaches infinity? And in some cases, we're also going to check and see what's the limit as x approaches negative infinity. So if I look at A, sine of 5x, what happens with sine of 5x? As x approaches infinity, what happens to the sine graph? It's oscillating, right? You're always in between -1 and 1. What about the denominator? The denominator is approaching infinity. If the numerator is always in between -1 and 1, and the denominator is approaching infinity, what happens to the whole fraction? Oh, so awkward. The numerator just goes between -1 and +1, right? But I'm dividing by bigger and bigger and bigger and bigger numbers. Doesn't the horizontal asymptote have to be 0? So wrong asymptote. Y equals 5x as x approaches infinity. That's a line. That doesn't have a horizontal asymptote. This guy over here, 1 over x minus 5. Denominator gets big. Whole thing goes to 0. not the asymptote I need. This guy here, 5x divided by 1 minus x. Yeah, there is a horizontal asymptote. The degrees are the same, but the horizontal asymptote here is negative 5. And so it's this last guy over here that actually does work. If you look at the degree 2, leading coefficients, you're going to get 5. Are all the friends mostly okay? Anybody go 12 for 12 last night? 10 out of 12 or better. I can deal with that. 9 out of 12? Okay, I can deal with that. I can deal with that. All right, so put that in the middle of the table. Please make sure your name is on it. And let's have a conversation about some indeterminate forms, shall we? Indeterminate forms. Who's got some for me? Okay. All right, Aaron, what was that first one? 0 over 0. Incoming. Are you going to catch it? Okay. So indeterminate form, 0 over 0. Aaron, tell me why this is an indeterminate form. I agree with you, it's the indeterminate form.
Because 1 you can't divide by 0.
Can't divide by 0.
2, everything divided by 0 is 0.
No.
No, wait, everything divided by itself is 1. I'll do that first.
Any number divided by itself is 1, so I might be applying that rule. Another one?
The numerator is 0, it has to equal 0.
If the numerator is equal to 0 and I'm dividing, 0 divided by number is 0. And then the last one is I can't divide by 0. So you've got like 3 different ways to argue indeterminate form. I need some others. Lewis, give me one.
Infinity over infinity.
Infinity over infinity. Give me some reasons why infinity over infinity has to be an indeterminate form.
The numerator and denominator are the same, so it can be 1.
Numerator and denominator are like the same. I want to put that in quotes because infinity, there's a whole lot of infinities out there. You might think 1, you might think infinity because infinity divided by number is going to be infinity. And you might think 0 because a number divided by infinity is 0. Everybody good? Those are 2. Those are the 2 obvious ones. These are the ones we've been dealing with forever. How long?
1 to the infinity.
1 raised to the power of the infinity. Mr. Link and I were actually just having a conversation about this one. Why is that an indeterminate form?
Because anything 1 is supposed to be always 1 no matter the exponent.
1 is always 1 no matter the exponent. 1 raised to any power is 1.
But since it's infinity, it should be infinity.
Because you're raising something to the infinity power, you're thinking infinity. Okay, other ones. Stephen.
0 to the power of 0.
0 to the power of 0 is an indeterminate form. Tell me why.
Because, well, if anything is to the power of 0, it equals to 1.
Anything raised to the power of 0 should be 1.
Yeah, and anything, well, 0 to the power of anything is 0.
0 raised to the power of anything is 0. Okay. There are more. Celeste.
0 times infinity.
0 times infinity, probably obvious argument here. 0 times any number is 0, but infinity times any number should be infinity. What else, Carmen?
Infinity minus infinity.
Infinity, you're getting a letter of recommendation.
Oh,
Do you
yeah.
need a lifesaver as well? Jeez.
Aaron.
Okay, I'll be sure to also include hungry as one of your adjectives. Infinity minus infinity. Good. At least one more. David, what else?
So what? Infinity to the power of 0.
Infinity raised to the power of 0. Infinity raised to a power should be infinity, but something raised to the power of 0 should be 1. Great. There's one more. Steven.
Infinity times infinity?
Infinity times infinity. How do we feel about this?
It's just infinity.
Not one of them.
It's just infinity.
Infinity times infinity. Trust the instincts here.
Infinity.
Should be infinity, not an indeterminate form.
Yeah.
Right, the issue with all of these, they're rule breakers. Right? There's like multiple rules that you could apply and you don't know which one is it.
Infinity plus.
0 to the power of infinity.
0 raised to the power of infinity is the last one, and here you go. There you go, work for it.
Ooh.
All right, if I could get everybody, including the camera, over at the laptop, we're going to go on a little field trip to the back of the room. Okay? It is importante that Stephen is able to see the screen since he represents many friends.
Hey, get out of the way.
All right. I apologize now. I'm going to put this in your head, and it's never going to come out. You're gonna hear this song for the rest of your life.
The song that was playing yesterday?
The what?
The song that was playing
No. All right.
Even worse.
Even better, you mean?
Even better.
Even better.
Better or worse? It's not a
All
matter
right,
of
better.
opinion.
It's my class. It's my opinions that count. I haven't written your letter of recommendation. Your opinion doesn't count yet. All right.
Hey, I'm told.
Here we go.
Yeah.
Here we go. Here we go.
I love Yes Prep.
Yes, prep connection.
Woo! Best Wi-Fi.
Just say
This
yes.
is what you call
Oh,
I really
education
like
connection.
is what it felt like to be in the
tested it
90s.
twice.
What it
The
felt
other
like to
option
be
is
in the
I'll sing it
90s.
to you all.
Yeah!
Video.
No, come on. Singing. Come on. We'll sing along with you.
You should do both. You should do karaoke.
Oh.
He didn't want to sing. He doesn't like to sing.
You gotta hit the play button.
Hit the hit
Yeah,
play.
Mr. DeRosa, come on, man.
Ah, look at that.
Hit plays.
The sound doesn't work. Suzanne, what are you doing?
This is like a song like we have to believe it for it to
Okay.
work. Oh.
Oh, God.
Indeterminate forms.
There's 8.
You gotta put them on.
There's 8 mistakes.
Oh man, it's so long.
Infinity, no do.
Stop. I don't like it anymore.
Focus on the video.
Alrighty.
What's up?
Woo! Alright.
One more time. One more time. One song you guys can make us.
And that is cover your head. I do think it's interesting how diverse that class was. There was one student of color, and she was right in the front.
Because diversity.
Because diversity. That's, I'm just saying, as much as I love that video, there is one student of color in the whole video. And she did a really good job.
Are we gonna learn that?
Are we gonna learn that?
Well, she didn't mean
I'm gonna try to teach it. I don't know if you're gonna learn it. All right, here we go. All right, there are 2 model problems that we're going for. My goal is to get through both of these so that you can do the homework and do the homework well. It's on page 7. All right. So first of all, have kind of conversation something here. Is model problem number 2 an indeterminate form? If so, which one? Is that an indeterminate form? Limit as x approaches 1 from the right, 1 over natural log of x minus 1 over x minus 1. Is this an indeterminate form? If so, which one? write on one that I didn't think was going to be so hard. Stephen, which indeterminate form?
It's over 0.
It's over 0.
Wait, 1 over 0. So,
Okay, you're taking the limit as x approaches 1 from the right. What happens with the first fraction?
0.
Natural log of 1. If you get close to 1 from the right, what happens to the natural log function? You're getting close to 0. 1 over 0 is infinity. Minus this guy over here. X gets close to 1 from the right. You're going to get 1 over 0, which has to be infinity. This is an indeterminate form. Infinity minus infinity, you could argue it's 0 because they're the same, not necessarily. A big number, infinity minus a number is infinity, or a number minus infinity is negative infinity. This is an indeterminate form. Everybody okay? But if you want to use L'Hopital, you got to keep in mind L'Hopital is really there for problems of the form 0 over 0 and infinity over infinity. So what you need to do is some algebra to get this into that form. That algebra that I would consider doing here, 1 over natural log of x minus 1 over x minus 1, get a common denominator. And that may not have been what you thought I was going to say, but get a common denominator. Okay, 1 over natural log of x minus 1 over x minus 1, your common denominator has to be natural log of x times x minus 1. To make this first fraction have the common denominator, multiply the top by x minus 1, multiply the bottom by x minus 1. To get the next fraction to have the common denominator, you're going to multiply the bottom by natural log of x, so you multiply the top by the natural log of x. Just some algebra. You okay with the algebra? Yeah, common denominator. Now, sometimes the algebra might help you get rid of the indeterminate form. But if I take the limit as x approaches 1 from the right, I've got 1 minus 1, which is 0, minus natural log of 1, 0. Natural log of 1 is 0 times 0 is 0. Good news, though. That's a good indeterminate form for us because we can use L'Hopital. Okay, so see what you can do with L'Hopital. X approaches 1 from the right. Don't forget that annoying little brother. Be careful when you're using L'Hopital. This is not. Did he take that? He called Hank. Did he take it?
No, he took it, he tested out of it. But still, he tutors it.
Okay.
I mean, yeah.
All right, derivative in the top, what is that? 1 minus 1 over x. Derivative in the bottom, I've got natural log of x times x minus 1. I got to be really careful here. Product rule. So I've got 1 over x times x minus 1 plus natural log of x times 1. Is everybody okay with the derivative stuff?
Yes.
Okay, take the limit as x approaches 1 from the right. What happens now? The numerator is equal to 0. The denominator, 1 over x times x minus 1. This guy is 1. That's 0. Natural log of 1 is 0. Bummer. So you know what you got to do.
Circle and answer and move on.
Circle and answer and move on. No. What do you got to do?
You don't have
Do it again.
You got to do it again.
But I simplify.
Right? You're going to use L'Hopital's rule again. So by L'Hopital, take 2. Limit as x approaches 1 from the right. Derivative of the numerator. Derivative of 1 is 0. Minus derivative of 1 over x. You've got that one memorized. Negative 1 over x squared. Derivative over here. Product rule again. Derivative of the first is going to be negative 1 over x squared. Leave x minus 1 alone. Plus 1 over x times the derivative of x minus 1 is 1. Plus the derivative of natural log of x is 1 over x. Evaluate now and see what happens. Take the limit as x approaches 1 from the right. 0 minus a negative, obviously, plus. 1 over 1 squared should be, what is that, 1? In the denominator, we've got, what is this, negative 1 times 0. Plus 1 over 1 is 1. Plus 1 over 1. Oops. Everybody okay with 1/2? Is everybody really okay with this 1/2? Myra, you're good? Colin, you're okay? My really quiet friends up front?
Oh, we good.
Okay, yeah, you know I was talking to you. North Central East End, we're okay? And all the friends in the back? Alright, so infinity minus infinity. Just do a little bit of algebra. It might involve getting a common denominator. That's great. Once you get to 0 over 0, once you get to infinity over infinity, not too bad. Sorry, had to go there. Not too bad. You get to use L'Hopital's rule. 0 over 0 and infinity over infinity. All right, here's one that's going to blow your minds. Here's one that you're just not going to see coming.
Are we going to go back to number 3?
Yeah.
If we have time, yes. All right, here we go. So we're on model problem number 4. And Stephen, I'm good if I move over here. Limit as x approaches infinity, 1 plus 1 over x to the x power. Convince somebody near you that this actually is an indeterminate form.
Oh,
It is?
That it is an indeterminate form.
it's the power of infinity.
Okay, so.
Oh, 1 over infinity equals 1 over 0 plus 1 over 1.
And I probably didn't give you guys enough room to work on this one.
Is that
There's an
what's the indeterminate?
yeah, how? I just don't want to.
Andrew, are you convinced that this one's an indeterminate form?
Maybe that's why it's indeterminate.
Yeah, make sure Louis convinced you.
I follow.
Convince me. You don't even convince me. Just convince me. Okay, but it's not just that. What's happening on the inside? Okay. Alright, so I was just having a conversation with Giselle, who has something like this on her paper. 1 over infinity, you guys know, is going to get to 0. 1 plus 0, 1. 1 raised to the power of infinity, indeterminate form. Alright, so now here's the thing. You are not going to see this one coming. The approach to this is not something I plan to assess heavily. It's going to be in 1 or 2 of the homework problems. This guy here, that was in the video, and they were like, oh, the worst are the exponential ones. These are horrible. Or really exciting, depending on how you are. LA was like, great, they're horrible. So here's what we're going to do. We're going to start off and say, let y equal this limit as x approaches infinity, 1 plus 1 over x to the x. I don't know what this is yet. I'm going to introduce a dummy variable. I'm just going to say, let me call it y. Why? Because this works. What you're going to do is we're going to take the ln on both sides. Take the natural log on both sides. 2 questions here. Number 1, is that legal?
Yes.
As long as you do it to both sides, these things are legal, right? Why?
Because
What might make you think take the natural log, Celeste?
because taking the natural log will cancel out the exponent. We'll be able to
Not
bring-
cancel out. That's not the word I wanted to hear.
It'll
Yeah,
bring
bring it down.
It'll allow you the opportunity to bring the exponent out, the variable out of the exponent. This is why we want to think ln, but we're going to have to be really careful here. So if we take the natural log on both sides, I'm going to say it's the natural log of y is equal to the natural log of the limit as x approaches infinity of 1 plus 1 over x raised to the x. I took the natural log on both sides. Lewis is like, oh my god, really? Yes, we're going to take the natural log of the limit of 1 plus 1 over x to the x. And you might think, but wait, the natural log of something raised to a power, I get to bring the power down in front? True, but you're not taking the natural log of something raised to a power. You have the natural log far removed from where the exponent is. There is a property of limits that says the natural log behaves nicely and I can switch these. This is a property of limits. So rather than taking the natural log of the limit, I'm going to rewrite this as the limit as x approaches infinity of the natural log of 1 plus 1 over x raised to the x power. This is all still equal to natural log of y on the left-hand side. This little switcheroo between the natural log and the limits is a legal thing. I'm not worried too much about convincing you guys that it is legal. Just know that it is. But the advantage now you finally get to use that property of logs that says, oh, I can bring the power down in front. So what we're saying is that the natural log of y is going to be equal to the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. I'm taking the limit as x approaches infinity. Have a quick conversation with somebody near you. What's going to happen?
You could just make it 1 over
Yep.
fraction.
What?
So basically, so like, I expected it would be.
Alright. Take the limit as x approaches infinity of x times natural log of all the stuff. What happens as x approaches infinity? This guy here?
Infinity.
Infinity. This guy here. This is where you have to do some thinking.
Make it
1
One.
plus 1 over infinity. This is 1. But I'm taking the natural log of 1, and the natural log of 1 is 0. Indeterminate form?
Yes.
Nice job. And a little fist bumping happening over there. So we've got infinity times 0. This is a problem. Unfortunately, this is not a problem that can be solved with L'Hopital's rule.
You circle it and move on.
No.
He's gonna teach us something else.
You need more cleverness. Infinity times 0 is not an indeterminate form. But there was something that we did yesterday, there was something in the video that they recommended. Infinity times 0, you want to rewrite this in a way that you get a fraction to show up. Aaron, what legal thing are you thinking about? You what? It hasn't hit you yet.
I know we have to do
Okay, all it is some algebra cleverness. Anybody get some algebra cleverness here? Stephen, what you got for me?
Do you convert 1 plus 1 over x to x over 2?
Whoa. Hold on. Okay. Limit as x approaches infinity. We've got x times the natural log of 1 plus 1 over x. I heard you saying you want to do something in here, maybe?
Yes.
1 plus 1 over x. You could get a common denominator. That could be good. That could be good, but then you still have infinity times something that's going to be 0. Multiplication in L'Hopital's rule is a problem. You need to get to division. Move what down, though?
Yeah.
1 plus 1 over x.
The 1 plus 1 over x, the problem is I'm taking the natural log. And I don't have properties for sums. It's the x that I need to rewrite. What we're going to do is we're going to rewrite this as the limit as x approaches infinity. What just happened there? Limit as x approaches infinity, natural log 1 plus 1 over x. Rather than saying multiply by x, I'm going to divide by 1 over x. First of all, is that legal?
Yes.
Right? This is like going backwards in time where you would think, oh, keep it, change it, flip it. I'm going back to that form because now look what happens. I've got natural log of y here, limit as x approaches infinity, natural log of stuff divided by 1 over x. Take the limit as x approaches infinity, and I've got, what is that, natural log of 1, 0 over 0. Indeterminate form, but this is the good kind. Now I can use L'Hopital. So take the limit as x approaches infinity. Now be careful here. Derivative of natural log of stuff is 1 over stuff times derivative of stuff. I need the derivative of 1 plus 1 over x. Derivative of 1 is 0. Derivative of 1 over x
Negative 1x squared.
is negative 1 over x squared. Now I come to the bottom. Derivative of 1 over x,
Negative 1 over x squared.
negative 1 over x squared. That's promising.
You
Yes.
have to use cancel out the negative one.
This negative 1 over x squared in the numerator, the negative 1 over x squared that's in the denominator, those guys cancel out. Finish taking the limit here. Limit as x approaches infinity of 1 over 1 plus 1 over x. You guys know what that is. Limit as x approaches infinity of 1 over x is 0. Plus 1.
1.
The whole thing is 1. Here's the thing though.
What about the
Yeah, 1 is not the answer.
One equals the
natural log?
Right, if you really follow the links all the way through, 1's not the answer. 1 is the natural log of y. So the natural log of y is equal to 1. What's y?
0.
Not 0.
No,
You guys are saying 0 because I think you're saying natural log of
Oh.
1 is 0. I'm asking the other question, the natural log of what is 1?
1?
No.
E.
Wait, E.
E.
Ah.
The easy way to do this is it's called exponentiating both sides. You raise both sides. You say it's e to that power equals e to this power. Because these are inverses and y is equal to e. But y, if you go all the way back to the beginning, the significance of y is the thing we were trying to evaluate. So that's like I planned it or something. So limit as x approaches infinity of 1 plus 1 over x to the x is equal to n. Okay. Tonight's homework, you should find 1 through 6 to be really straightforward. I think all of them are set up as 0 over 0, infinity over infinity. 9 through 12 are going to push your thinking a whole lot more. I'm going to be here today from 1:30 to 2:30 if you want to work on test corrections, or if you just want to work on homework and get it done. Or if you just want to spend quality time with me, David, that works too.
Alright.
Okay?
You guys might not remember, but when you guys first learned E last year, or the second time, I showed you that formula, and I was like, just believe me. That's what he is.
Now you don't have to believe him anymore. You can believe me. And L'Hopital.
If you like L'Hopital, tap your hand.